My name is Peter, and today we're going to talk about distributed journey. So this is who am I, and first and foremost, I'm a software engineer. Recently, I even found a job, finally. So I joined Nethermind.io. We are a small team working remotely on Ethereum client, so it's a blockchain thingy, and we are using .NET Core to implement. So I could say that I'm working with decentralized system on a daily basis. And let's talk about this distributed system in general. Mostly microservices, but not only microservices. And I have 45 slides. We have 45 minutes, but this is pure coincidence, this 1-to-1 ratio. So this graphical comparison, to the very left, we have the centralized system. So we have a single node, single source of truth that does all of the processing, right? Then we have the centralized system. So we have multiple nodes. It can be 2 nodes, it can be tens, hundreds, thousands. And like the main distinction is that in a decentralized system, each node is pretty much the same, right? And it makes decision on their own. But in order to create this aggregated response of the whole decentralized system, we usually need some form of consensus, right, to reach this state. Like we have in blockchain, and we're, for example, mining transactions, we need some consensus to decide which transaction is the best. Or like we have distributed databases, and we have replicas, we need to decide which one is a master or which one is a slave. And to the very right, we have a distributed system, and simply by looking at this picture, you can tell that decentralized is a subset of distributed, right? So in a distributed world, we have also many nodes, and they work usually with each other, right? So the business logic is usually spread between different nodes. So for example, we have service A, B, C, D, and so on, and they all need to work all together in order to fulfill the user's request, right? So this is like this general comparison. And now, before we begin, if you are really new into this whole distributed world, you should probably start with a monolith, and you should probably stick with the monolith, because it's usually the best approach. But if you decide that you really want to distribute your system, what you can do, how you can start. So start with the monolith, and then think about cutting into smaller pieces, like, so this is sort of modular monolith. Now, if you are into domain-driven design, you can think about bounded context, you can think about techniques such as event storming, and Mariusz Gil, I think he's here, so he could tell you about it. So with these techniques, you could think about splitting your monolith and your big domain to smaller domains, extracting bounded context and extracting microservices. Or you could also look for some bottlenecks within your apps. Like, let's say you have a process that takes a lot of time to compute, so you look where it happens, and you extract it. And you can extract it to background job, into system service, daemon, whatever, and then eventually you can implement external independent service. Next. There's a lot of challenges, but there are also good parts. But let's start with the challenges. So if you just start with implementing these services that are distributed, on the day one or a few days later, you will face a lot of challenges that you will have no idea about when you start doing systems this way. So starting with some obvious things like internal communication, routing, load balancing, service discovery, and then getting into asynchronicity, because this is where all the fun parts start, with the asynchronicity, and well, all of the issues start to also happen and show with the asynchronicity, right? And we'll see how we can deal with those using some patterns or some tools. And you will also need to do this mental switch as a developer and realize that data redundancy is usually good, especially in distributed world. And I will also show you, I will talk a little bit about distributed transactions and how you can deal, for example, with letting your end user know what's going on with your request, because it's also not that obvious. And also we'll talk about some tools that you can use. They are free and open source tools that you can use in order to create this robust system. Okay, but there are also good parts, besides challenges and the issues. So the good parts are that since our microservices will have their own unique domain, they will be independent and they will be autonomous. I mean, they should be if you design it in a good way, right? Because you could also have so-called, not the modular monolith, but this monolith, this is sort of decentralized. So you just have monolith that is spread across different nodes, but under the hood, they are all talking to each other. And this is your single issue with monolith, just spread n times. So it's not that way. You shouldn't do it that way. But given that you design your system in a good way, you will get these autonomous applications, right? And they will be easily replaceable pieces of the bigger system, and there is no like real definition of a microservice. For example, Jeff Bezos said that there will be a team of maybe 5 to 7 developers that should be fed with 2 large pizzas, which is of course questionable. This is like a team that could work on a service. And the other definition is that it should be something that can be rewritten from the scratch in about 2 weeks. These are some of the definitions. And the great thing that it comes with this separation is the asymmetric scalability, because you can extract this single part of your system that is, for example, takes a lot of resources like CPU, RAM, time to compute, to finish. And then you can scale it, add hundreds of instances of the service, and your system will work all the time and will be very responsive. And with this, all these things come resiliency. And since you should have like a separate repository for a service and maybe a separate team for a service, and they can be, of course, written in different technologies, which is also a good thing. They'll be also deployed at its own pace. So there will be no this we release tomorrow thing, right? They can be all released independently from each other. Okay. Now, what can go wrong? Like a lot of things can go wrong, but this is one of the things that can go wrong at the very beginning, especially when it comes to failures. So what a typical microservice would be, right? So it would be an autonomous app with its own domain. It will probably have their own repository, maybe a separate team to work on it, and it will deal with this specific business logic, of course, and it will subscribe to these particular messages, right? So we are talking about comments, events, and queries, and we are talking about subscriptions on a message bus. We are talking about comments and events. And usually it will provide an API that will return the data to some other service that is, for example, needed to fulfill the user request. So for example, we could have 10 services, orders, products, invoices, and the order service can have its internal API so that API gateway can fetch the orders and return them to the end user. This sort of thing. So just a typical HTTP API, I would say, that are just spread. Now, let's start with API gateway. So API gateway is an entry point to your overall solution, right? So if you are working on a web application and you have the API and you create your robust RESTful API, or maybe HTOAS, level 4 maturity, or whatever you call it, right? This is your entry point to the app. And we have the same thing in our microservices because we don't want our user to have an idea that, look, we have 10 or 100 services. This is URL 1, 2, 3, 4. You have to authenticate to each one, and you have to call 10 services, and then you can transform the data to get this object that you really want, right? This is like a concern of the API gateway. And all these things, these cross-cutting concerns like authentication, authorization, maybe some internal load balancing, service discovery, all these things are responsibility of the API gateway. And of course, we don't have, I mean, it's not like we need to have only single API gateway. We can have API gateway for PC app, for the desktop, for mobile, and for other things. But we want to have this abstraction so that end user only calls this single endpoint instead of having an idea that there is 10 or 100 services living under the hood, and he has to call each one separately. And this is how this API gateway could look like. This is my side project, but we can either implement it on our own as a separate application. We can use some services like Conc Gateway, API-G. We could also set up API gateway, for example, using Nginx. So it's really up to us how do we want to achieve it. Now, where the fun part starts with asynchronous messaging and asynchronicity in general. So this is a sample screenshot of RabbitMQ. But of course, we can use Rabbit, ZeroMQ, Kafka, Azure Service Bus, whatever services that suits your needs. But yeah, we want to have some sort of message broker, right? So we want to achieve the following thing. What we do not want to do is to build a synchronous HTTP facade. And what does it mean? Well, I've seen projects that under the hood, they have this event stream. So they have this bus. So that the services under the hood publish events, right? And this is fully asynchronous, and it's great. But the API gateway, what it does, it just says, okay, I get this command from the user saying create product. So under the hood, the API gateway calls post synchronously to another service. So it's not really what we want because there is still this synchronous calling, right? And if this command takes a lot of time to compute, then it can blow, right? Because there will be many synchronous requests. And this is not what we want to do. Of course, we can do it, but this is not what we want to do, given that we want to have like a truly asynchronous system. So our API gateway should send the request to the message bus, right? Just push it into this queue and return to the end user with some response. And by doing this this way, our solution will be responsible all the times, because the only responsibility of API will be either to fetch the message using HTTP call, or just put the message into the queue and just it doesn't care what's happening. So either we are putting message into the queue, or we are asking for data. And if you want to ask for data, we shouldn't use queues. I mean, if we are fetching the data from other service, we should do it synchronously, because you might try to be the smart guy and think, why not, right? Why wouldn't I put this get products query into my queue? I'll be like 100% asynchronous, great. But imagine the following: you have your message bus, and you put this query into the queue, and then your queue might be busy, it might be down, or your service might be down, whatever. Your user browses the web app, and 5 minutes later, out of nowhere, he gets your product list, because the queue just processes your message, right? So this is not what you want to do. You want to have your data, like fetching the data asynchronously, or maybe some pushing it via WebSockets, but not really asynchronously and using the queue. So this is how a typical subscription to the commands could look like. Let's say I have some service. It's responsible for creating some products report, and is subscribing to different events coming from different services. Next, so as you've seen on this picture, I've put here some message contracts, right? So it can be classes or some other structures, depending on your language. And my services subscribes to these messages, right? So I need to define somewhere the messages contracts. And well, messages flow through our system. They are usually unique. So we have message, for example, command called create product, and we have event product created or product created failed or whatever. And we might get tempted to create so-called common utility helper package, because being a good developers means we are aware of dry principle, right? So by following the don't repeat yourself principle, when we spot the same piece of code 2 times, and I don't even want to say 10 times or even more, we would immediately extract it and put it into some helper package, right? And it makes sense if you do it maybe for some infrastructural things like database providers or caching mechanisms that you don't want to re-implement in each of your service once again. But if you're doing message contracts, these are just like POJOs, POCOs, just anemic classes like getters and setters, nothing else, just simple data transfer objects. So what you do instead is just copy and paste everything. So if I have my, let's say, reporting service and is interested in this order created event, I shouldn't have any reference to this order service or some other packaging repository. I should have the same structure defined in my service, and then just subscribes to this one. Because, for example, if I'm using some messaging queue, I can usually set a routing key or exchange name, and it will fetch the messages that are interesting to me, right? And it will serialize, deserialize into the structure that I really want them to be. So avoid this dry, at least here. Make your services really pure, right? With no references maybe to some small utility packages, but don't define your contracts in some single repository or as a separate package for each of your service. Don't do any dependencies here. Next thing, we have the correlation contents, and what it is. Now imagine that you're sending to your service a message A, let's say create an order. And this message A, or this sort of request can be very simple, like we have a command and the command is processed and it produces an event, like 1-to-1. Or it can be something much longer, like we have the message A, then it produces event B, and the message B produces message C, and so on and so on. So it can be like 10 messages under the hood. Now, how can I track back who originated the request? I need to have some way to do it, right? So there is this thing called correlation ID, and this is actually a very simple concept. So I could either assign to each of my message this unique ID, let's say it could be some string or GUID or UID, and the API gateway, when it gets the user request coming to the API, it could assign this unique ID, and it will be passed with each message through our whole process, right? So we can easily track back who originated the request, and yeah, that's it. We can get this traceability very easily. Or we can also have this separate correlation context. So it can be any type of metadata that is being sent along with our messages. I can put their ID, user ID, his headers, whatever I need, right? And within my handler here, I will get my, for example, comment or event to process, and I will also get this context with this metadata that I'm interested in. Next thing, what do we do when our handler fails, right? Let's say we are doing some logic here in this place, and there is an error, right? And what can we do about it? Well, it really depends what this error means for us. Because, well, the simple solution is to just put try catches everywhere. Within our handler, we can do this fancy try catch jQuery thing, like have this interface with on success, on error, on failure, all these nice methods. But we can do something a little bit better. So assuming that we know which exception means for us, that this is maybe some business logic exception, or this is an exception that was generated by the database that was temporarily down, or other service not responding because it was restarting, we could check for that exception, and let's just auto-retry. So if my handler fails, and for example, it turns out the database was down for this short period, or the service was not responding with the data I'm interested in, it doesn't mean that my business logic failed, right? I should just retry it, and if after 5 retries or 3 retries, it's still not responding, I will just put this message either into some dead letter queue, or I will just throw an exception, and maybe someone will take care of this because there might be an issue there. So don't fail immediately. I mean, you should fail fast if there is an issue, but this is like pretty common that your services are sometimes down, that your resources doesn't respond at all times. So we might need to retry, and maybe after a few seconds it will be back again, right? Instead of just failing immediately. Now the interesting part, and this is really a tricky one. So how is my API request doing? And we have this typical Jon Snow scenario here, because once we send our request to the API, we have no idea what's going on. So the user sends a request to the API. And given that our API is truly asynchronous, and we are not asking for data, so we are not doing GET request that can be just redirected to another service, and our data can be returned back immediately, what we can do? Well, I could maybe return him 202 accepted, and say, hey, I got your request. Thanks. Right? And the user is like, okay. Now, how can I tell if my request has completed, if it succeeded, if it's failed, whatever happened, right? So we need to wait to return the state of this request to the end user. And of course, it's purely optional, and it can be done in multiple ways. So one scenario is that, let's say you are there is some e-commerce, and you click on create order or complete an order, and maybe after a few minutes you will get an email saying order completed. So it can be one way of letting your user know that his request completed or failed. But if you want to have a responsive app, let's say you're building another Azure, and you want to have this nice UI when you can see that there is a new VM being created, like we are installing Ubuntu for you, like we are updating your OS kernel and whatever, right? You want to have this responsiveness on your web application or desktop application. You can really send an email, right? You need to somehow let your user know what's going on with his data. So for example, here you could use WebSockets and maybe just push this data for him. So in order to do it, I need to have some separate service that will track my request. So this service could subscribe either to all of the messages that are being sent through our overall solution, and maybe to some small set of these messages. And for example, this service could for example subscribe to create order or other created messages. And then when it gets create order, it will just send to the end user something like, I got your create order command and it's in pending state. And once he gets order completed, then he will send him back, your order has completed, and I'm sending you this info that it completed, right? So on your application, you can show order completed, right? So this is how you can handle that. And this is one of these things that is not obvious once you start implementing your distributed system. And it can be really tricky. Next, data distribution, right? Because one of the advantages of having distributed services is that each service can be implemented in its technology that suits its needs, and each service can have its own database, right? We have different databases. doing different things. So we don't need to have this single SQL cluster that can become a bottleneck, and maybe it doesn't make sense to store logs in SQL database when it should be NoSQL. So at first we need to say hello to eventual consistency, right? Because once we put something into the queue, we can be sure whether it gets processed right away or maybe in 5 minutes. So we can be certain that maybe our product or order is already in the database and we can fetch it. And as it turns out, we need to make this mental switch, right? It turns out that in the distributed systems, this data redundancy and duplication usually is a good thing. Why? Because it makes our services more resilient. And how it happens? Well, imagine that you have your order service, once again. And your order service needs to have a list of products, right? So maybe instead of asking your product service all the times when it gets some message like create order or order created or anything else, when it needs to get these products and calling synchronously through HTTP your product service, which introduces a thing called temporal coupling, which is not a great thing for our services because the service can be down for the time and our order won't be created. What if our order service can have this products collection in its own internal database? So even if the product service is down, we can still, for example, create an order maybe, or maybe the other way around. If our order service is down, we can still list the products or anything else, right? So we can spread this data, and by doing so, we can make our services more resilient. And this is one of these ways that you really want to design your system so it can still work, at least partially, even if some other service is down, right? Because it can work separately without this service A, B, C being up and running at this time. And with data distribution and all these internal communication things also comes this CAP theorem, right? So we are aware that the network partitioning is a brutal truth. So there will be always some delays, some downtimes, and we have to deal with that. And our services will eventually die. And we need to be resilient, and we can be resilient by doing this asynchronicity, right? And publishing comments and events and subscribing to them, to these types of messages. And also by providing this these databases that are separate for each service and having this internal collection of data that we are interested in instead of asking synchronously other services at all times. And of course, patterns like retries, circuit breakers, and all of that also come into play with these things, but this is usually something being handled by our API gateway, right? This is why you have this gateway, so even if our service is down and we can't get data right now, maybe you have this retry logic that will ask for the data in 1 second once again, and this data will be already available for our end user. Okay, internal communication. Now, usually when we are thinking about communication, we are thinking about HTTP. So we have service A that wants the data from service B, so it calls it via HTTP. And now the question is, should the service A knows where is the service B? Like if it's dynamically changed IP, or if it's dynamically changed DNS or some internal URL, should we have hard configured these settings? Well, we could, but it doesn't scale well. So instead, we need to add some service registry. And there is this nice tool called Consul. Anyone use Consul? Heard of Consul? Okay, so nice. So I'll be talking mostly about free and open source tools here, because there are, of course, some paid services. And Consul is one of these tools. There's also Stack from the Netflix that does the same things. So basically, it's a centralized registry. So when our service starts, it will just register to a console under the group. So let's say in our console, I will have a group called product service. And the product service, whether it will be instance 1, 9, 95, or 100, it will register to this product service group. And now when my API wants to get the data from product service, it won't ask product service directly at first. It will just ask console, hey, give me the list of instances of product service. Okay, here it is. And then I will ask maybe first instance to get this data from a product service, because I will be certain that this service actually is there available and I can ask him for the data. But this is how the console looks like, the web panel, and this is very easy tool to use. But we can make our life even easier, because under the hood, console also provides some load balancing. But in the service, you would have to call console, then pick some instance that is currently available, and then ask the instance for data. we can use Fabio. Fabio is a load balancer and it was created by eBay, so we can assume that it's quite well designed, right? And then Fabio is built on top of Consul. So right now, instead of asking the Consul for the list of instances, I will just call from my API, gateway or service A, I will say, I want these products from this product service, and what I will do, I will just have my Fabio running, for example, on localhost 9999 instance, 99949 port, right? With this /orders or product service that will be routing my traffic to the product service, and I will just call this endpoint from my API gateway, and it will get the data from me, right? It will internally manage all of the load balancing and service discovery stuff, and it will be that easy. I will just call the URL like I would call from my HTTP client, just do a GET request here, and doesn't care about anything else. So this is how the Fabio can look like. We have the routing table, we have the service groups here, and we have these endpoints that we can call our service internally to get the data. Next thing, Saga. Anyone heard about Saga? I think some of you did. So this is really quite an old concept. I think has over 30 years and was published by some paper on a university, if I remember correctly. And basically, Saga helps us to deal with these distributed transactions, so we can get rid of these two-phase commits because it doesn't really scale well. It's not really the best approach. And usually it's mixed up with Process Manager, but Saga sounds more sexy, of course, so everyone is calling this thing Saga. Well, basically, Saga is a sort of message router. So internally, it has no state, while the Process Manager may have some internal state. And what it does, so Saga can subscribe to messages, right? Because imagine the following scenario. Let's assume that we have this process called complete an order. And it can be easy, complete order or completed, like one-to-one comment event, or it can be something longer, like I will call my product service with reserve products command, then I will call my invoicing service, my payment service. There'll be 10 messages in this overall flow. And now, whose responsibility is it to take care of it? What if something happens, right? Should the order service care about rollbacking the failed message sent or email sent, like a notification? Well, no. So we need some external tools, some external service that will be aware of this, right? So we'll have these distributed transactions there and describe it, and it will either subscribe to these commands and will be aware what should I call next, or if something fails, I will just call this compensation action, so I will roll back. So let's say I have 1, 2, 3, 4 step. There is the step number 4, and there is something bad happens, and I will just roll back 3, 2, 1 back, right? And of course, we can get into some edge cases here. What happens when our rollback fails? But I think that's a different topic. So, but you have to be aware of that in distributed world, also your rollback can fail. And this is some sort of Saga. Like we have, for example, here order created, order revoked, and so on, like different types of messages that I'm interested in. And this Saga knows if this messages gets here, I will just publish another comment or another event to another service that will know how to do with this in order to achieve this process. Okay, now the secret storage, and it's not really dedicated to distributed services, it's more like a general question. And usually when I ask people, maybe by doing some workshops, where do you keep your credentials? I get usually 3 answers. First is, it depends, it's very neutral. The second one is everywhere. And this one is, you don't want to know, right? So, yeah, they put it everywhere in environment variables. They put it into app settings, into their private repository. They are just spread everywhere, and maybe there are some, some elder administrators that are aware where this configuration is. So we need some place to keep our credentials safe. And again, we have a lot of tools. We have Azure Key Value Storage, Azure Key Vault, and other things. But all of these tools is Vault, and it was also created by HashiCorp that created Consul. It's free to use, and basically it's a centralized credential storage. It can use Consul under the hood, but we can also have a lot of different integrations, and it provides us this sort of actually vault that we can in which we can put our configuration and just ask for our configuration and load it when our application starts. So this is how the vault looks like. We have the panel, we have either key value storage or, for example, nice JSON editor, and I can just save my settings there and say to my app, hey, when you start, just call the vault for your app settings and update your configuration. So I can easily change it, restart my app, and get the new configuration again, right? And it will be kept here in the single centralized place, and it will be quite safe. And other things, so logging, monitoring, alerting. Again, when we have multiple services, or even we have, let's say, monolithic app, but it's decentralized, so we have multiple nodes, we probably don't want to have some things like logging to a file. We need to do some logging maybe into an internal centralized database. But again, why would we have our own database and create our own tools to extract those logs, right? And if you are brave enough, you can work with Elasticsearch. So you have ALK stack, which is great, but it's also quite heavy to use because it requires a lot of resources. So you have to put a few virtual machines to get this cluster up and running, so it can cost you some money. And besides logging, it provides all these tools for generating these fancy charts. You can do a lot of data manipulation here. So the logging is just one part of ALK stack, right? ALK stack. It's just one thing. But maybe let's make our life simpler. If I want to just do logging, I can use tool that is dedicated for logging. So for example, in .NET, .NET Core, or some other languages, I could use a simple logger, like let's have Serilog, Log4net, Elma, or something like that. And then this log can save the data, for example, to a sink, which is like some database or a file. And I will have a tool that will be able to extract these logs and show me these logs on some dashboard. So one of these tools, for example, is SegFault, but it's I think mostly for .NET, but it also runs through Docker. So each of my service will have this sink, so it will send these logs to SegFault, and SegFault will provide me this real nice dashboard, and I can browse through the all logs coming from all different services. I can query them using this syntax that is provided here, something like very simple SQL. Okay, same things with logging goes to monitoring and alerting. So again, we need a single centralized tool for that. And what we can do about it? Well, our services can return some sort of metrics. And again, we don't have to do it on our own. We have libraries for that. So for example, for .NET Core or .NET, we have app metrics. We just plug it into our app, and it's already providing a metrics, like CPU, memory usage, whatever you need, right? And these metrics are provided in a format that are understood by other tools that are already on the market and are free to use. So some of those tools that are pretty well known are things like Grafana, that provides a very cool dashboard. I'll show you a screen in a moment. We have InfluxDB, which is a time series database for storing our metrics. We have Prometheus, which is for alerting. We have Jaeger, which was created by Uber and is also open source. So these all tools are free to use, and you have libraries that you can simply plug into your applications and just plug these tools. And for example, when I add this app metrics to my .NET Core app, so it will start returning these metrics, and I will start the InfluxDB with Grafana, I can get this nice dashboard, and it doesn't cost me really that much of work, maybe an hour or two to implement, and I can have this nice screen put in my room, and I can just, look at this dashboard and be proud that I have like 0% of errors coming from my app. So this is all free to use, and you can use it really, really easily by just plumbing your system using these different tools and services. Next thing being continuous integration and delivery. So we can also do this old school zip and upload, and I think it still can work in some companies maybe. But given that we want to distribute our applications, I think we would have to make our upload tool have multiple endpoints, so we can upload at one time to many different places. But given that we have each service in a separate repository, so each service will have its own pipeline, we can, for example, define the Docker images for each service, and we can get this basic pipeline like build, test, pug, publish, fetch, deploy, and let me show you on these screens here. So here is my code. I do a git push. Sorry, there's the GitHub, this black cat. I should be the white one. For example, it builds and tests through some service, build service like Travis, Jenkins, Upwire, whatever it is. Then my build service creates a Docker image, and it pushes this into some Docker registry, Docker Hub, Azure registry, or your internal Docker image registry. Then I have the orchestration tool that knows that there is a new image, so it can fetch it and redeploy my app and just update the image. So I can have this seamless integration. I will just commit, and my app will be there up and running in maybe a few minutes. And speaking of orchestration, so we have to deal with the fact that Kubernetes is everywhere. And actually, I was thinking about getting PhD at the university one day, but I didn't want to do it with Kubernetes because I just browsed through this documentation, and it's really, really a pain to go through it. Maybe one day I'll get to that. But you can either stick to maybe pure Kubernetes. You can use paid services like Azure Kubernetes Service, OpenShift from Red Hat, but you could also give a try to another tools that are free to use. And one of these tools, okay, there are two tools that I'm aware of. So one of these is Portainer. It's a very easy to use tool. Under the hood, it uses Docker Swarm for replication and for distribution. But Rancher is much more advanced. And recently they released a version 2.0. So Rancher is built on top of Kubernetes, something like Fabio is built on top of Consul, and it provides a very nice UI with some additional features. So we can leverage the power of Kubernetes, and we don't really have to either pay to Azure for its AKS or to Red Hat for the OpenShift, but we can achieve the same things, I would say, with some open source and free tool. And we don't really have to dive into this plain Kubernetes shell. We can do it mostly with this nice UI. So this is Rancher, and I suggest you maybe give it a try. The next time you'll be thinking, how can I actually deploy my services and what tool to use to have this orchestration. There's also this new kid on the block called Service Mesh. I only scratched the surface of it, but as I'm aware, Service Mesh is mostly all about internal communication. So we can imagine that we have Service A and Service B, and Service A wants to maybe talk to Service B, and it either wants to talk via HTTP, or maybe it uses some gRPC to stream the data under the hood, and we need to have this circuit breakers, retries, all of these sorts of these policies. So we get this resiliency, we get this retries under the hood. Now we can implement it in each service on our own, or we could use a thing called Service Mesh. So for example, we would have a service A, and there would be like a separate, for example, smaller service called Sidecar running within our Service A instances. And if we are asking for example, from Service A or Service B ask us for data, it doesn't talk to us directly, it just talks to this Service Mesh. So this Service Mesh takes care of all these potential failures that can happen under the hood, like this retries and all these things. And yeah, the great example is Kubernetes. So if you look into Kubernetes, how it's built, then each service has this sidecar, and all these services internally communicate, for example, through gRPC protocol, and they just talk to each other through this sidecar, which actually creates a service mesh. And I've seen there is already on Azure new service, I think called Service Fabric Mesh or something like that. So it's already on Azure. That's the next step. I think microservices are not so cool anymore. It's all about service mesh right now. But there is more. There is more things just to finish this presentation. Besides the microservices that maybe you work on a daily basis, there is a whole different world. And I'm not talking about SOA. I think we are past the SOA. And I would like to tell you very briefly about blockchain, because I've started working with blockchain. Now, I don't want to do this typical blockchain thing. I mean, have you ever been to some blockchain lecture? Because usually what happens is that someone opens the website, right? And on this website, you have this particular.js background. You have this default bootstrap template. There is this input where you put some arbitrary characters, and there is this hash being generated, and someone tells you this is blockchain, and this is disruptive, and this is the future. So I'm not going to do this here. I'm going to talk briefly about some other things that are more interesting. So blockchain is a centralized solution. So as you've seen on this picture in the center, we have like multiple nodes. They are decentralized. So we have, for example, thousands of nodes. And one of the examples of blockchain is, for example, Ethereum that I'm working with. So it works as a global virtual machine, and on this virtual machine we can run apps. They are called decentralized apps, DApp in short. And of course they are spread all around the world, so even if we take down 100 nodes, there's still whole network up and running because there's thousands of nodes. So if you like to take down the whole network, you would have to destroy all of the nodes at once. And there is a lot of challenges when it comes to blockchain. Same as we have, for example, in databases. Let's say we need to reach some consensus within our databases. Which one is master, which one is slave, right? Which one saves the data, which one just gets the data, to which one we can write the data. So we have like different types of consensus here, like which transaction is the valid one, like which transaction should we accept. All these things relate to internal communication, just like we have within our microservices and all this service mesh stuff, this internal HTTP communication. We have the same issues there, but on a different level. We have things like Ghosty protocol and some peer-to-peer protocols that you might know from using maybe BitTorrent. So it's here. And if you've heard about Cosmos DB, this nice database created by Microsoft, we have IPFS, which stands for Interplanetary File Storage. So this is actually a distributed database that stores parts of files on each node with hashes, so we can easily track down which file you want to download from each node. So I would say Cosmos DB is like, compared to this one, is not a thing. And all these things related to some hardcore math, like new SHA-3 implementations, or some cool things like zero knowledge. Now, this is, again, some old concept from mathematics. I think it has also about 30 years old. Now, but imagine the following scenario. You want to prove someone that you know something, but you don't want to reveal your secret. So, for example, you want to prove to the server that you know the password, but you don't want to tell the server what is your password. Or maybe more realistic scenario, you want to prove to the IRS that you paid for the taxes, but you want to reveal the IRS how much you paid or how much you earn. And these are the things that you can actually achieve with the zero knowledge things. And this is just a pure mathematics. And this is all these things that are happening in this blockchain. But for now, I mean, I've been to the blockchain conference in Prague a month ago. And if you think the JavaScript world is immature, you haven't seen blockchain world. Trust me. I mean, JavaScript compared to blockchain is just mature as the C++ long release implementations. I mean, this is nothing. But it's getting more stable now, so there is more things to use. But I mean, if you think there is, this page is last days since JavaScript framework, so it will be like last hour since blockchain framework, I think here, but it's getting more stable. But just to sum up, maybe you watch the Silicon Valley show, and all this goes towards this true decentralized internet called Web3. So if you watch this Silicon Valley show, there is this idea about creating decentralized internet, and this is one of the things that blockchain is trying to implement. So I just want you to be aware that besides the services, microservices, service mesh, all this stuff, there's also this different world that has to deal with this decentralized system as well. Now, thank you very much. You can scan this code, and it will redirect you to my website where you can find all of these links. But if you want to have these slides, or maybe you want to get the slides, you can just go to this website, go to events, and you will find the link there, so you can download it, or you can just scan it right away. I don't know if we have time for any questions or not. Does anyone have any question? Yes? Mm-hmm. In terms of scaling, so again, you could use, for example, paid services. For example, in .NET, we have this thing called Signal Air. Or I think in Node.js there's Socket.io, but I heard that it's probably not the best choice, but I'm not the Node.js senior programmer. So if I want to scale, I would just scale this single service. But if I don't want to really care about scaling it, I would probably use, for example, Signal Air paid service on Azure, and I wouldn't care about this issue with dealing with multiple connections that are long-lived. But that's a good point. I mean, as I said, this WebSockets and pushing information thing, I don't know if it's a good idea to actually have it running for all of these scenarios, maybe for some subset of your system. But yeah, again, it's always gaining some benefit, but it costs you some money, right? So yeah, that's true. I'm sorry, I didn't mean the schema registry, because you could use, for example, Avro if you are using Kafka. That's fine. I mean, what I meant is that you shouldn't have these packages, like binary packages, with your classes that you would share through all of your services. You know, just like, for example, you would use npm or NuGet or some other packaging system and add a reference to it. I mean, having like maybe JSON schemas is fine, but if you have these binary compiled packages, it can become quickly a dependency hell. You should just have your schemas on your service, and you could just copy and paste them and maybe update them in their own pace for each service. That's what I meant. Okay, I think we're done here, so thank you very much.